Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today we got a Class D amplifier. Yes, another Class D. I picked this one because I like the large parts on it, large inductors. It's beauty on a Class D amplifier is when you have a good LC filter output stage. That's where the digital meets the analog. So we're trying to make an analog signal out of a chopped up digital signal, Class D, right? So efficient. I mean, this heatsink right here does all the work, so we're going to see how well that works. I'm going to get the thermal camera out, and hey, by the way, if you like that thermal camera, if you've seen it before, it's a nice thermal camera. I have a link down below for that. They got the next generation out, which, God, I'd like to get that one, but I'll put the link down for that one, so it's even nicer than the one I have here. But this board looks really nice, nicely designed, nicely built. So, and it has a TPA3255 from Texas Instruments, which I think is just a generation of these Class D chips that is getting better and better. And I'm really interested in what my friend, the audio guy, he's into rock and roll, and I built him a Class A amplifier. I want to build this one up, see what he thinks about this one, because I think it's promising. It's got some nice parts on it, and let's come over and take a look. We're going to do a Borbede plot of it, see how flat the curve is. I expect it to be pretty flat. These Class D amplifiers usually have nice flat curves with good phase response. One bad thing about some of the Class AB amps I see, or even Class A's, is they roll them off too much at low frequencies and roll them off too quick at the high frequencies, which the problem with that is it changes the phase. The phase starts to change before you start seeing the gain change, because the phase is going to change 45 degrees at the roll-off generally. So yeah. And another thing is, if an amplifier will go out to 20 kilohertz or beyond, say 40 kilohertz, 50, 100 kilohertz, which these things are designed to go all the way up to 100 kilohertz. I don't know how far this one's going to go, but what that means to me is that it's a very fast amplifier. If it can go to 100K, it means it can respond quickly. So I like that. I like that idea. So let's just take a look at the Borbede. We're also going to run power, see how hot that heatsink gets, and let's come over here and do it. Oh, and by the way, I'm going to have a link from Amazon down below. It doesn't cost you anything to use those links, and it helps the channel and helps me buy more of this stuff. I've got, geez, a lot of stuff around here, but this is one project I want to work on, and let me know what you guys think of this, if you guys have any experience with this particular board. But yeah, it sounds promising. So, alright, let's do it. Alright, and this is the way the board comes in this plastic heat shrink, so kind of protected that way. And in the box had foam where these terminals are kind of protruding. But yeah, you can see they're very nice terminals that this thing has. Nice, robust, nice size coils. You can see the size next to my fingers. If we're looking at millimeters, about 20, looks like about 27 millimeters across, about an inch across. They're the kind of red cores, and I guess I could count how many turns, reverse engineer them. 75 working volts for the capacitors, 4,700 microfarads it looks like, so a half a farad for each one. And yeah, nice gold, it looks like gold plated terminals. Nice bulky beefy guys. Alright, let me get this plastic off, we'll get a closer look, okay? Alright, there's a close up of the board. Now one thing I want to show you is I backed out these terminals. They don't come all the way off like some do. Also, these are designed so that you could put the board right between these two plastic pieces, so, and then it insulates it from the board. But in this case they're using the board, so that's how they did it. And there's some little eyelets there if you want to put wire down in there, or use banana jacks that go on the top. Now up here in the top corner, you can see right here there's a part number. It looks like LM2575. That is a switching regulator, and here's a linear regulator, LM317. So you got some voltage regulation going on here. sure this inductor is working with this switcher here. And I believe you're creating 12 volts off of this from this switcher here, and probably maybe a 5 volts from this guy, I'm assuming. And up here we have a couple ST op amps where the input comes in. Each input goes through an ST op amp. Okay, and it looks like a GZ316 is the part number on those. And we got all these 10 mic caps here. Okay, here's our fault LEDs. We have one for the one to the right here is for clipping, and this little one right here just says fault. So I'm assuming that's over voltage or over current or over temperature, probably any kind of fault. And you can see all the ceramic capacitors. Now these capacitors here, down on the board, that's really hard to see down in there, it says 3300 microfarad, and they've chosen to put 4700 microfarads on the board, so that's nice. And looking through this inductor on the output, I can see a 1 microfarad capacitor value. So these white capacitors are polypropylene 1 microfarads. And looking at the inductor, inboard in-circuit measurement, of course, but it looks like it's about 10.8 microhenries. So I would probably believe that. Now, let's see what frequency. Let's go to 100K. Alright, 100K, 11 microfarads, and it looks like about 150 milliohms, 153 milliohms. Now, just to confirm, on the board shows a lot of values besides the reference designators, which is nice. But it says 22, and these look like 10 on the capacitor. Just want to measure it. In-circuit capacitance measurement. And yeah, they're more like 10 microfarads. So I think that's the 10. I didn't know if this is for 10 volts or 10 microfarads. Alright guys, I want to take the heat sink off, so I haven't taken it off yet. You're going to see it the first time with me. Oh, I'm losing some washers though. But I took the screws off. They have little plastic washers, and they were just barely hand tightened down. I mean, just very softly, so I'm going to be careful to put them on nice and square. And alright, so here's the grease on the heat sink. I think I'll probably apply that evenly. And there's one of the spacers, the little nylon washers. I'm sure they're one on each side just to space it so you don't crush your chip below it. So you can see it sits on this little bar up here. And then we have all these nice fins. So if you have low airflow, that's going to help a lot. And here's the TPA part. It says TPA3255. You see the nice heat sink slug on the top of the chip for heat sinking. And one thing I want to point out is right here says L and L. So that we're using ferrite beads, these nice size ferrite beads right here, to bring the power into that chip nice and clean. Alright, so let's go over the setup here. I got input power coming in here, okay? And so this is our input plus or input return. I don't want to call everything ground because every return is called a ground, then it's really gets weird because not every ground's tied together. They're all returns. Now the return here on the input power and the return to the left and right channel are tied together. Here, let me put this on ohms. So they are tied together here. So these, whoops, see, there we go. There we go. So the input power return and the input signal return are all tied together, so that's good to know. But the output returns are not tied to the same spot. These output returns to the speakers are tied to somewhere separate. So I'm going to put this up here. We're going to monitor voltage with this meter. Okay. My generator, my signal is going to come from my oscilloscope. We're going to do a Borbede plot. So its return and the scope, looking at the input, is tied. These grounds are tied to the same thing on the scope, okay? And the power will be, they'll all be tied together, but the output will be floating basically. So Bridgetied configuration to the load. So basically we have two drives here, and neither one of them are ground, you know, reference to these. These are return and plus out, okay? So this right channel this left channel. So we're going to power the right channel, and I got a differential probe on the output. So my scope is not tying these things together. So I'm using this Pentec up here, DP25, for the output reading, okay, times 20. So there we go. Scope's going to put a signal in, it's going to read the signal out, and it's going to give us a Bode plot. Okay, we're going to be using the GW Instec for the Bode plot. And so channel 1 is coming in, that's the input signal. So I got that in millivolts, 200 millivolts per division right now, okay? And it's set at 2 milliseconds. Now once we do the Bode plot, the scope will set it all up and do it automatically. But on our first power up, we'll look at our signals, and I'll manually inject a signal, so we'll be able to see the input, the sine waves, and see how what the input and output looks like to each other. So here's the output right here, okay, channel 2. I'm going to push this in so it's right underneath channel 1, and it's going to be at 2 volts per division. Alright, so let's go down and power it up. And well, here, let me just show you this. By the way, channel 2 is a differential probe. It's 20x. We're AC coupled, full bandwidth, all that. Channel 1, 10x probe, AC bandwidth, full bandwidth. Set up that way, okay? Now we're going to go down and look at the board and watch this power up. Alright, I'm going to bring up the power supply voltage, and we're going to power this thing up without an input signal to begin with, and we just want to make sure that everything looks okay so we can start, okay? So I'll be watching the current and the voltage as I turn it on, okay? Okay, we're at 0 volts. I'm bringing it up right now. And the good thing is, once I get at 1 or 2 volts and I don't see any current flow, I have a good feeling that we don't have any shorts or anything like that. So I'm at 6 volts, 10 volts, 12. Okay, I don't see any, okay, 19 volts. I see about 100 milliamps. So everything looks good. I'm at 35. Okay, so I'm up around 40 volts right there. And we're only about 80 milliamps. Okay, now when I come down here, I see both red LEDs on, which makes me wonder. Like, I don't know why they're on. That looks like a fault condition, and I don't know why we'd have a fault at this point. Alright, so here's our input signal, 200 millivolts peak. So it's 200 millivolts peak and a negative 200 millivolts peak. So we've got 150 millivolts RMS, okay? So that's our signal, and here, let me turn on the power supply. Okay, there we go. And they're in phase and all that. Everything looks good, right? So the interesting thing is, here, hold on a second. Let me set up some readings. All right, I've got the reading set, 140 millivolts in, almost 4 volts out. All right, so you know what? Here, let's get this generator output a little bit higher. Generator 1. Okay, let's get the amplitude a little bit higher. Okay, so alright, we're 7 volts here. Let's go just a touch higher. We're 500 millivolts peak to peak. So we're 200 millivolts per division. 2, 4, looks like about 500 millivolts peak. That's about right. And the output's about 8 volts, 8.3 volts RMS. So right there, we're about 8 watts output. And everything seems to be good. So both red LEDs are still on. I don't know, I don't understand. Maybe when they're both on means they're good. When they're off, they're bad. Because right now, everything seems to be working and they're on. Incidentally, the power's in is 50 volts. Let's drop it down to 48. That's supposed to be the max. Let's drop it down there. And we're 0.28 amps in. Okay, things seem to be working pretty good. Alright, so what I've done is I've turned off the input signal. So this is just the input voltage, 48 volt, 0.08 amps. So that's 80 milliamps. That comes out to about 3.8 watts, 3.84 watts. And when I put the signal on here, let me turn the signal back on. Okay, now what we're getting out is about 8.6 watts, and our input power is about 13.4. So that seems about right. I mean, it's 8.6 watts out plus the 3.8 watts to is essentially overhead. That comes out 12.45 watts just to be running right now. And so we're only losing about 1 watt in efficiency. So pretty darn efficient. Everything looks good. Okay, let's come over here and look at our output. There's our input and our output right there. Everything looks good. Everything, 48 volts going in. Yeah, everything seems to be operating well. Everything's really cold. Cool to the touch, of course. We're only dissipating about 1 watt in inefficiency. Alright, so let's set this up for a Borbede plot. And we'll go to the app menu, app. We're going to rotate over here, frequency response analysis, which is that guy. Select it, yes, we want that. And there we go. So, analyze. Okay, so setup. Input is going to be channel 1 in this case. And output will be channel 2. And generator, we're going to go from, I think 20 hertz is as low as we can go. Can we go 10? Yeah, 20 hertz is as low as we can go. And we'll stop at 1 meg. No, well, it says 500K. We'll stop at 500K. And let's see, amplitude, we're going to go, we're going to do the 500 millivolts, just what we just got through testing. 500 millivolts peak. And that gives us, yeah, let's do that. So I think we're all set up. And all we have to do is run it. So let's go ahead and run it. Okay, I'm going to zoom in on the screen so we can just watch it as I run it. Alright, so let's just say run. Okay, I guess I hit the channel 1 button. I just turned it back on again. FR run. Alright, the other thing is I have to go back to acquisition and drop it down to 10K. I don't know why it just doesn't do that automatically. That kind of a pain that I always have to go back and redo that. Okay, there we go. Now up here you'll see channel 1, the yellow, channel 2, the blue's the output. Alright, I had to plug the power supply back in, so we're going to start to run it again. And yellow is the input, blue is the output. So they look, at the low frequency, they look out of phase just slightly, and the phase is red, so we see that because, let's see, 0 degrees is over here, so we're actually out of phase a little bit, which you can kind of see that up here. The scope will automatically set up everything, so it'll keep on adjusting this so we can see the frequencies. Now, gain is the blue, and that should stay pretty flat. It's dropped off a little bit at the low ohms, but you know, it's pretty flat. You know, it's not like we're getting it rounded off at the low frequencies, right? It's coming off at 20 hertz pretty flat. Just a little bit of a dip. And you can tell that because the phase was also changing. So the phase is going to come down here. See, here's 0. Now these are going to automatically adjust as you know, the curves come across. They're going to auto adjust. So right now 0 degrees right here, and we're coming down to 0. So it started off right around 30 degrees. Now this is right around 8 watts output. Normally this is done at 1 watt. This is kind of a standard, just compare amplifiers to each other, but we're just doing it 8 watts, and we're going to see, I think, good results. You can see that they're in phase up here, which this is coming close to 0, so that's going to be in phase. And also you can see the signals look really clean. and our gain is going to be really flat. We're going to see how far it comes out. I think it's going to come out to 100 kilohertz, but I'm not sure. Let's see what happens. Okay, I'm going to shut up here, and I'll speed this up in post-processing. One thing to mention is down here it actually tells you your gain and phase at any particular moment. And this tells you the frequency where you happen to be at. Alright, that was interesting. While this continues writing and finishing off, we're at 20K, 30, 40, almost 50K. There's a hard filter, digital filter inside this thing that just cut it off. So we went real flat out to 20, 30, and 40, went up a little bit, 40 to 50, and then it just dropped off. And then the phase went, you know, kind of crazy after that too. So the gain just dropped down to 0, and then the phase, you know, there's not much phase because there's no signal. So that's why this is all crazy. But yeah, I started seeing this little slope, like there's a filter going on, but then this looks like a digital filter where that just cut it off. So that's kind of interesting, right? Alright, I did one more sweep just to make sure that we got the same thing, which I knew we would, but here, let me go to this button here, and then we can go to FRA measure. Let's turn on the cursors. Cursor 1 is right here, the input. Okay, I'm going to leave it right to the far right, 20 hertz. Take cursor 2, I'm going to move it to 20 kilohertz. And that's about 20K right there. So we can see 20K minus 17 degrees. 20 hertz is plus 25. Okay, and the gain is 27.8 or 28.4. So the gain is really flat during that, and the phase drops off just a little bit. If I take cursor 2 and go in, you can see it say 10 kilohertz, it's minus 9, and then from 10 to 20 it goes from minus 9 to 16, so change about 6. And then if I go up a little bit higher, it's about minus, okay, 0 degrees here, that's 2 kilohertz, and then 3, 4, 5 kilohertz at minus 5 degrees, and then let's come out here, so right about there it's 10 degrees just after 10K, and 20 at 16 degrees, so not very much. And now the input, let's go to cursors 1, let's see where that 21 degrees drops down. We're dropping in 15 degrees at about 30 hertz. Okay, we're about 10 degrees, and that is about 52 hertz. And see when we're at 100 hertz. At 100 hertz, we're about 5 degrees. And then it's just a few degrees above through most of it until it starts dropping negative. So, you know, the phase is pretty darn flat too.
Alright, so a quick look at the data sheet from Texas Instruments. First, I noticed it's last dated 2016. That's not too far away considering. And it does not show that it's end of life or not for new designs. So that's great. This is a current product. And here's the applications here in the right corner. Over here on the left, this is what we want to look at. Here's the power ratings. Now, see this 10% T-sheet plus N? Yeah, okay, fine. But I'm really interested in stuff at 1% or less. 10% is when you start to get clipping and distortion like that. So down here, it looks like more like 260 watts into 4 ohms. And that's in the Bridgetied load configuration, which we have on this board. And 150 watts into 8 ohms. So 150 watts into 8 ohms. That's a very fair rating, I think. I think that sounds good, actually, because it's not overrated. Now, 10%, 185, so it's not that much. So we want to just keep it down in the 1% range. And so here's some information about the advanced integrated feedback design. So this helps keep what they call the pure path or the ultra HD high definition. Signal bandwidth is up to 100 kilohertz. So that's, it's capable of going wideband, which means it's probably a fast, amplifier. And ultra low THD plus noise is 0.006. And again, this is typically rated at 1 watt and at 4 ohms, so that's, that's pretty typical. And 0.01% THD plus and 2 clipping. So, and it says less than. Now, PSRR is power supply rejection ratio. So, noise from the power supply, this thing's going to reduce it by 65 dB, which is really good because every 20 dB is a 10x factor. And they typically do this at 1 kilohertz. These things, even this THD is probably, well, I think the 0.01 is out to the 20 kilohertz, I'm assuming, from looking at curves and that. And so, and signal to noise ratio 111 dB, so that's pretty low. Okay, now here's the voltage range. Now, first of all, efficiency is 90%, which is awesome. And right above that, I kind of skipped over. It says pop free startup and stop. So has a design so you don't have those pops. There's loud, pops when you start or stop. And the input range, you can go from 18 volts to 53. On the board, it says 48. I think they're just trying to hit near the top. I think it's probably, if you really want to get the full power, you want to go close to 51, 52 volts probably. But 48 volts is going to get you real close too. Okay, so this curve is THD based on power. So here's that 1 watt spec. This is usually where they spec them, right here. But look, at 10 watts, it actually looks like it drops from 10 to 100 watts. It seems like it's, maybe at the bottom of the curve. So the 1%, so the 1 watt rating comes right across here. It looks like it's about the same as the 100 watt rating. So that's pretty darn good. There we go. And the red curves for 8 ohms, the black curves for 4 ohms. I mean, this looks like really good operation to me. And here's our setup. So we have our audio source coming in left, right. See, we have capacitors to take away the DC. And there's some signals here for clipping, reset, fault. And over here, the power supply shows it 51 volts and 12 volts. And on our board, we saw that we had a 12 volt regulator switcher. So, and then we have our LC filters going out to our speakers. So there are 4 outputs, but it's Bridgetied. So 2 outputs is being used for one, and 2 outputs is being used for the other. So we have a left and right channel. Okay, and that's what the chip looks like as far as the pin out. And you see there's lots of ground pins over here and over here. So they kind of space them around the chip. There's probably a ground plane inside the chip. See this thing that says thermal pad, this dotted line? This is a big thermal pad. So pretty good sized chip. All right, and here is the BTL, Bridgetied load, and this is our setup here. So again, THD 10%, these last 3 are 1%. So again, here we are 155 watts, and that's if you have 53.5 volts coming in. And here's signal and noise and all these other specs right here. All right, so here's the distortion based on frequency. And on the top left, you see 1 watt is black, 25 is red, and gray is 150 watts. So you can see the higher wattage after you get past 1 kilohertz, it kind of increases and it kind of peaks around, what is it, 2, 3, 4, 5, 6, 7 kilohertz. Still under 0.1. It's still about 0.06 or something like that, that peak, I'm guessing. And over here it shows with an auxiliary filter, you can get a little bit smoother line, but the distortion is pretty low. Now this is with 51 volts coming in, and if you go 53.5, you can see it lowers just a little bit over here. Okay, now these bottom curves are based on, power, like how much power and distortion. So kind of like what I showed you on the first page. And so, yeah, kind of similar stuff. So either, whether you have power or frequency, across frequency and power, it seems like it's going to be under 0.1. I mean, looks pretty darn good. All right, so now this is Bridgetied load. And now this shows you, your rail voltage here, and how much power you can expect to get out based on these ohms and this voltage. So let's say you're at 45 volts, you can come up here and you're going to get about 140 watts out at 8 ohms. And red ohm, the 4 ohms, it's about 180. Okay, so that's this curve, and this is based on the 10%. So we like this one over here to the right. So let's say we're 48 volts. Well, let's just say we're 48 volts. We're going to be right up here. It's going to be still about 125 watts, 8 ohms, and the red one, the black one, the 4 ohms, is going to be about 225. So, and that's at the 1%. This is the temperature at 75°C. So this is after it's warmed up. Okay, these curves here, this shows efficiency, and this is efficiency here on the vertical, and our wattage across here at the bottom. And this is when you're doing 10% distortion, so this is when you're pushing it. And same over here. So this is when you're pushing the amplifier. And it's just showing the power loss that you can get here on the vertical graph versus your power output on the bottom here. So let's say if you're putting out 300 watts, and it's 4 ohms, you're going to see, if I come up here and across it's 55 watts of dissipation that I'm losing on my board. So that's why I gotta, my heat sink and everything has to take care of that. And this one down here in the bottom right is our FFT. And it's showing how many points they took, 16,000 points. And they're showing they have really low noise floor, around down here to minus 140. That's pretty incredible. This at 4 ohms. And then we have one spike here, and this looks like it's at 1 kilohertz. So this is a 1 kilohertz test frequency at minus 60. So, yeah, that looks pretty darn clean. All right, so this is a functional diagram, they call it, and these are the 4 outputs here, the 4 inputs here on the left, and the stuff on top is the control circuitry and, all the fault circuitry and all that kind of stuff, and the voltage regulator and all the housekeeping type stuff. So here I'll zoom in so you can see a little bit better, and I'll come up here at the top. Okay, I'll come up here, and then I'll come down here so you can see the signals. Now see, each one of these channels is going to be the same: gate drive, some FETs, and so on. So yeah, just 4 channels. We're using 2 of these channels as a Bridgetied load. So that's how it's bridged, because we're bridging between the 2 FETs inside this driver and 2 FETs inside this, and that gives us our bridge. And here's the system block diagram. Okay, now here I'll zoom out so you can see the whole thing. Okay, now here's all the system stuff up here at the top again. The inputs right here, A, B, C, D. We're going to have a single input for A and B because we're Bridgetied like this guy is over here. And same here. And see, here's 51 volts and 12 volts coming into the system. And we've seen that on the board, the little switcher. So there you go, zoom in on that part. All right, and this is the actual schematic diagram, a typical schematic diagram of a Bridgetied load. Yeah. All right, zooming in on the schematic, Now you can see a little bit better. 12 volt circuitry up here on the left. Our input for A and B channel here, 10 microfarad caps, decoupling DC, just leaving the AC left. Same here in channels C and D. And then we have our fault stuff. You know, this has over temperature, clipping, under voltage, it has everything. So lots of different fault protection. And then the output, you see the LC output. This is the common mode configuration where 2 caps go to a ground. But the speaker is not referenced to any ground. This is just the filtering here. And so here's one Bridgetied load from output A to output B, and the other one's output C to output D. And there's and some of these caps are used for the drive circuitry. They're charge pumps to give voltage for the FETs to turn on the high side FETs. Now, here's some of the fault handling, the pin-to-pin short circuit, over voltage, under voltage, and fault handling. So it talks about that stuff there. And over here we have the signal clipping of pulse injector circuitry, and the DC speaker protection. So it protects from DC voltages going to the output. So there's lots of protection. Now, one more thing I wanted to point out on this wattage thing is down here, this 2.5 watts. This is just when you're idling. Nothing's happening. It takes a little bit of power to run things. It's 2.5 watts. All right, and this is another important table. This one shows thermal information. Over here, the top one's resistance junction to ambient. So this is that little thermal pad on top. So without that, just using a PCB, you get 50 degrees per watt dissipation of the device. And with this, you can lower that to 2.4 watts per degrees. You can get that 2.4 degrees C per watt. So, and you look at item number 2, it talks about the packaging. So the junction decays, it's only 0.3. So let's say you have 10 watts being dissipated inside the chip. It raised at 3 degrees. Okay, so you have to you have a heat sink on that top, and then you can really efficiently pull the temperature, the heat out of the junction of the part. Now you just have to get it off the heat sink. Okay guys, I've got this set up so I can inject a signal into both channels, and I've got 8 ohm load on each channel. I've got 2 differential probes on the output now. This one is going to the mix sig, and let me just show you that. That is right here, the DP1007, and it's sitting on top of the Pintec, which is going to this channel. Okay, so and also I'm using the Unity generator to inject a signal. So I've got everything right here. We're going to start off with 1 kilohertz, and I've got about 700 millivolts right now RMS coming into it, and that's what we're going to do. And then right here I've got the mix sig scope, so we can see the waveforms. Now the center waveform is channel 3. Okay, all right guys, so the mix sig channel 3 is the input, so that's the purple waveform right in the middle. You can see the signal right there, and the measurements down here, 717 millivolts RMS, frequency 1 kilohertz, and the other 2 channels are set at 10 volts. Whoops. Okay, these other 2 channels are set for 10 volts per division, and so that'll be our outputs. Okay, what I'm going to do is I'm going to bring up the power supply, and all right, I'm zoomed in on the mix sig. So again, we'll see our 2 different channels here. I'm going to bring up the power right now. Okay, I'm almost at 16 volts, and I think that's where the output gets activated. Yep, right there, 50, just under 16 volts, I believe. And I'm at 20 volts, still increasing. We're going to bring it up to 48 volts, maybe 50 volts.
Okay, we're at 42, everything's stable. I'm at 48 volts there. And I'm just going to bring it to 50 volts even. Okay, so 50 volts, 1.5657 amps from the power supply is about 7 to 8 watts. And each channel is putting out about, let me see, 36, almost 37 watts. So we are pretty close to 74 watts. So we're 4 watts lost in heat or whatever. So there's our signal. Okay, I'm going to go ahead and creep up. Now actually I'm going to have to drop these output signals because you can tell we're going to be off the screen. Okay, so I'm going to bring up the amplitude. Oh, and look at that, it goes into protection. So right about there, I'm at 27 volts almost RMS output, and then just above that it drops off. And you know what that is, guys? I just noticed my lab power supply is over current, so I got to bring the current up on that. I thought it was a chip protecting. Okay, I just maxed it out, so let's see what we can do now. I see a little noise, a little distortion, and that's right around 32 volts RMS, and we're starting to clip right after that. Okay, so if I drop it right there, we're at 27 volts and it looks pretty clean. Let me get the THD meter on this. Alright, so let's go ahead and bring up our signal again. THD is 0.005 right now, or 0.0, it's kind of bouncing around, but pretty low. Okay, we're at 0.02% maybe. And okay, so we're at 2455 volts RMS, and we're about 0.26% distortion is what I have. And we're 0.3% right there. And you can see it's starting to get a little, you know, high frequency noise on top. It's about 0.5% THD, and that's 0.9. Now there's 3.7. See, that's what I mean by there's 6.3, 8.7. So there's about 10%. That's ridiculous. So coming down here, that's about 0.5, and that's about 0.3. And look at that, 0.27. And there's the 0.27 from the Keithley. Now I don't have the best, you know, setup, so it's probably going to be a little bit lower if I really tried to clean up my leads and all that stuff. Alright, so we're about 0.27, and that's, you know, that's like 91 watts aside. I mean, I think that's pretty darn good right there. But 91 watts, and we still have some headroom to go. And let's go look at the board. And there's the board right there, and the heat sink's starting to get a little bit warm. Ooh, it's starting to get hot actually. Inductors are nice and cool, and I got my thermal camera. Alright, you can see things are starting to heat up. It's over 100 degrees on that heat sink, it says, at the hot spot. So yeah, it's getting pretty warm. You're going to need a fan to run this at high temperature RMS. There's the load over there. There's one load, and here's the other load right here. Hey guys, what do you think? It looked pretty flat, the Borbede plot, right? At the low frequencies, it was nice and flat. The phase looked good. On some amplifiers, you'll see somewhere around 100 hertz, or maybe just a little bit lower than that. They'll kind of come up and start amplifying, but they roll off at the low frequencies because of the input filter. Well, with the big 10 microfarad capacitors on the input of these, we get some pretty good low frequency response. At right around 20 hertz, it was already, you know, almost full gain, so that was nice. Phase didn't shift too much. At the high frequency, these digital amplifiers, these Class Ds, seem to roll off really sharp. Oh, so it's almost an ideal curve. Very good low frequency response, and also at 20 kilohertz they go right out there, and then at 30-40 kilohertz, you know, somewhere around there, they just drop off. often in Class ABs, you start seeing the phase, shifting away. You get that 45-degree phase shift at the roll-off frequency, usually just around 20, just beyond 20 kilohertz. But yeah, these Class Ds, they seem to have a pretty, pretty close to ideal frequency response within that audio range. So that's a cool feature of them. Also, the efficiency is really nice. That heatsink did get really hot when I was putting out, over 90 watts per channel. So that's like 180 watts this thing was putting out, which is pretty incredible when you think about it. It's just crazy. So very efficient. And the heatsink, the fins are almost an inch tall, about 3/4 inch tall, I'd say. So I think with a little bit of airflow, you could really keep that heatsink cool. So I'm going to continue this project with this board. I'm going to get a power supply. I've got to decide what power supply I'm going to get. What do you guys think? Either a transformer, do it linear, or a switcher. Kind of tempted to, I'm going to look at both ways, but yeah, I'm going to put a power supply. The nice thing is it only requires a single voltage, 48 volts. Well, around 50 volts would be nice. So we're going to look into a power supply for this, put it in a box, and see maybe a small fan, a nice quiet fan that turns on with temperature maybe. So yeah, we'll work on this project. All right. So hey, meanwhile, 2 thumbs up to the patrons. Appreciate you guys. And you can become a patron for as little as $1 a month. Links down below. Also, I've got these t-shirts now, and I think my wife's going to come up with some other designs. If you guys got any ideas on designs, that'd be cool. But we're going to do some t-shirts. The link's down below. And so that'll be neat. That's another way to help the channel. But thumbs up is a free way to help the channel. It really does help the YouTube analytics, so appreciate that too. And wow, enjoying using the meter from Dave. Thanks, Dave. Really appreciate that. I'm going to do a review on the 121 too coming up. But oh, by the way, if you like these differential probes, the MixSig or GW, any of the equipment I'm using, I'm going to have links down below. I've got a whole bunch of links for that kind of stuff down below too. And, it doesn't cost you anything. It helps support the channel. So appreciate all that help. And God, I'm finally glad that I'm healthy again and ready to kick off and start getting some projects caught up this year. God, yeah, I was down for a couple weeks, but yeah, I'm finally feeling better. So, all right, thanks guys for watching. We'll see you next time.